Hi, good morning. Today we are going to talk about wireless sensors and their connection with LoRa and LoRa WAN. The topics for today are going to be a few words about low power wide area networks, a few words about LoRa, a few words about the devices that support LoRa, and what means LoRa WAN. The general idea of a LoRa network is that we have several sensors, the ones with the red dots over here. These sensors can work on battery. They should have a lifespan of around 2 years with the same battery, and they are able to transmit information to some gateways that are somewhere between 1 kilometer to 10 kilometers away. Data that is transmitted to these gateways is afterwards connected to the internet from the gateway to a network, to a standard IP network. So basically a LoRa network means several sensors that are scattered around and some gateways that collect these information from these sensors and put it on a network. Remember, it needs to be a transmission at around 10 kilometers, and the lifespan of the battery for the nodes should be around 2 years. Okay, so a few words about LoRa. LoRa means long range, and it is a radio frequency transmission method that allows devices to consume a very little amount of power and transmit information over a long distance. This means that devices can transmit a small piece of information at some big interval of time using very few battery. LoRa is operating in an open frequency, so even though you are transmitting information to more than 2 kilometers, it's okay doing this without any license. So you don't have to pay a license to the state to be able to make the transmission. If you think of any other transmission method, like the GSM for instance, GSM operators pay a huge amount of money to use the frequency. Because of this, LoRa is operating in some frequency bands that are free, that are called ISM, Industrial, Scientific, and Medical. And these frequencies are different from continent to continent, and we are going to talk about this in a few. First of all, a few words about the radio frequency spectrum. So you can see here you have a graphic with the radio frequencies that are being used, from the extremely low frequency to the extremely high frequency. The frequency bands that you should be familiar with are the 2.4 gigahertz and the 5 gigahertz frequency. These ones are used for wireless. It's on your wireless routers at home. It's again an open frequency, and you are able to transmit information on those frequencies without paying a license. Usually this transmission is done over a few hundreds of meters. A wireless network would work maximum at 1 kilometer. But anyway, these frequencies are open, so you can use them without paying a license. For LoRa, the frequency is called the sub-gigahertz frequency, and it's operating somewhere around 800 to 900 megahertz, and sometimes at 400 megahertz. As I said, the distance is over a few kilometers, and there are some limitations. Advantages of open frequencies are that you don't require a license and you are free to transmit any way you want. The disadvantage is that you will have interference, because the same way as you can transmit information, anybody in the world can do this on the same band, and you might actually clash. And the data rate is pretty low due to this. Because of interference, data has to be retransmitted pretty often, so there's a great deal of issues with transmitting the data. So data rate is low. Compared to the GSM network, which is licensed by the network operators, that one, they are the only ones that can transmit in that frequency. So there's no way that somebody else can break the frequency and clash the transmission with them. So this is a difference. That's why when you have a mobile operator, you can transmit a great deal of information without having any interference. But the costs are of millions of dollars to buy a license over there. If you have any questions here. So keep in mind, this is an open frequency transmission. No license, but low data rate. The ISM bands, so the open bands that are used today, are the Wi-Fi bands and Bluetooth, 2.4 GHz and 5 GHz, and the LoRa frequencies, which are 415 MHz, 868 MHz, and 915 MHz, depending on the continent that you are on. This is really important because you need to configure your chip, and it's a really big problem if you break one of these frequencies and you use one of these frequencies in a continent where it's not allowed. So be aware of this. When you look at the world map, the United States is using the 915 MHz band, so be careful, don't use the European bands in the US. Europe is using 435 and 868 MHz, so do not use the 915 MHz frequency in Europe. You actually might go to jail for this. So be careful. Asia is using 780 MHz. Australia is using 435 and 915 MHz. South America is 900 MHz, and Africa is 435 MHz. So when you're using LoRa, look at the world map and read the frequencies that are allowed in that part of the world, and use it accordingly. So be very, very careful. Don't use the US frequency in Europe. Most of the chips are able to use any frequency, so you have to set it by software. Some of the chips are already constrained to the area where they are being sold. The chip that we have is capable of doing both the US and Europe frequencies. So for us, as we are in Europe, we are going to use 868 MHz. When it comes to the transmission, these are the parameters, the basic parameters for the LoRa transmission. First of all, it's the frequency. So you need to choose a frequency which is in the free band. So look at the laws in the country where you are reside and where you want to use this, and you have to set the frequency accordingly. The frequency band is divided over 8 or 15 channels depending on the part of the world. The transmission power varies greatly from the area where you reside. Again, this is something that you need to read in the laws. So in Europe, you can go from 2 to 14 decibels, and in the US, it's from 5 to 20. So be careful at this. Obviously, the higher the transmission power, the longer the range of the transmission, but the shorter the battery life. So it's a trade-off. For the bandwidth refers at how much data you can send in one transmission. Standard bandwidths are 125 kHz, 250 kHz, and 500 kHz. This is the bandwidth that it is used to transmit data around the frequency that is being used. So if you use frequency X, this is the bandwidth from x minus delta to x plus delta that is being used for transmitting your data. The lower the bandwidth, the greater the battery life, and the easier the transmission is. The higher the bandwidth, the lower battery life, shorter range, and more interference, because you are using a larger spectrum and the possibility to interfere with somebody else is greater. In Europe, you are allowed to use 125 and 500. In the US, I think you can use all the three of the bandwidths. So again, read the laws for this. The spreading factor. The spreading factor means how the information is spread across the bandwidth. The larger the spreading factor, the longer the range, like the distance where you can transmit, the shorter the battery life. So when you choose the spreading factor, be careful to understand exactly what is the range that you need to transmit in, and choose a spreading factor that is accordingly to this. Otherwise, you will drain out the battery. Remember, you have devices that should live 2 years on the same battery. The coding rate. The coding rate means how many error correction bits do we add for 4 bits of data. So the thing is, the transmission is going to be with errors. Because it's an open band, you can clash with other transmissions and there's a lot of interference. So receiving devices will try to correct the data at the receiver in order to extract the correct data and not to ask the sender to send it again. The more error correction bits you have, the more battery you use, because you need to transmit more data, and but the range is longer. So if you have more error correction bits, you can send data over a longer range, because data arrives with errors, but the receiver is able to correct more errors at a longer distance. Is this clear? Any questions? So there's a lot of parameters, but these are the most important parameters that you need to keep in mind. When we are going to set up our LoRa sensors, these are the parameters that you will have to supply. Okay, so let's talk a little bit about the devices. LoRa devices, basically the LoRa device is only the LoRa transponder. That's a little chip, usually made by Semtech, which is able to receive information, usually on SPI, and send it over the air to another device. So LoRa means just sending data. Usually the LoRa devices that you can buy come with a transponder and bundled together with a microcontroller. Why? Because usually you will have a sensor. So you have some device that is sensing the environment. It is connected to a microcontroller. The microcontroller does some basic processing, usually signal filtering, and then sends the data on the air using LoRa. If you only have the LoRa transponder, then you have to buy a different microcontroller, connect the transponder, connect the sensors, so on and so forth. Most of the producers bundle this together. So they will bundle a transponder, a microcontroller, an ADC probably, and the microcontroller will have GPIO capabilities. This implies that you have a chip where you can connect directly sensors, do some amount of processing, and send the data to another device. In the LoRa terminology, we have two types of devices, nodes and gateways. The nodes are the small devices that have the sensors connected, and all that they do is usually sense the environment and send some data, or receive some data on LoRa and do something in the environment, like blink a LED or something like this. They are always slave devices. They never they initiate communication with the gateway, but only at a certain interval of time. When it comes to the gateway is usually a powerful device. It's connected to the power source, so it's not on battery, and usually it's not in a very remote area. The role of the gateway is to receive LoRa data, meaning it will scan several frequencies, several channels, and receive simultaneously a lot of data, and send the data over an IP network. That's the normal network that you know, and sometimes the internet. So these nodes communicate via LoRa on the air with the gateway. The gateway receives the information and sends it over to a server on a network. From this server on the network, you can view the data on a website, or you can view it on your phone, but usually this is the case. Now, the network is really interesting. You have several nodes and several gateways. When one node is sending data, several gateways will actually receive that data. So when you make the transposition over an IP network, you need to be careful, because you might get the same data several times. LoRa is an air protocol, and whenever a device sends, a gateway will receive the data. Is it clear? So nodes and gateways. These ones don't work on batteries, so don't worry about power consumption. Okay, here are some LoRa nodes that you can buy. The one that we are going to use is the LoPi. It's basically an ESP32 microcontroller. It's capable of Wi-Fi and Bluetooth, and also of LoRa in both frequencies, 868 MHz and the US frequency 915 MHz. So this one is okay in the US and Europe. Just be careful when you set the frequency. Don't mismatch them. You might get the police on your door. I'm serious. You are doing transmission over 2 kilometers. So this is not legal if it's not in an ISM band. It has 4 megabytes of flash. and this is useful not for the program, but this device can connect to several sensors, store the data on the flash, and send it via LoRa when it can. And the best part of it, it's programmed in MicroPython. So you don't need C programming, you just program it in Python. And it's really, really easy to program. This thing is around 20 bucks, 20, 25 bucks. The second device that we are going to use for gateway is the LoRa GPS hat. This is designed for the Raspberry Pi. It's a LoRa chip, and it's directly connected to the Raspberry Pi, and it has also a GPS chip. This one is usually used either as a node, either as a gateway. It knows all the three frequencies, like both European and the US frequency, has LoRa GPS, communicates via SPI with the Raspberry Pi. This one has no processing power. It's just a sender. It's just a transponder. You need a Raspberry Pi for it. For this device, you can find also the version for Arduino. So these ones are the most common that I've seen. Third one, we have one from Microchip. This one knows only the European frequencies, and you need to buy another chip which knows the US frequencies. So be really careful when you buy this one. You might buy it for the wrong country. It's similar to the LoPi, programmed in C. It has a PIC microcontroller, and it's also capable of LoRa. Another interesting node is the WASP mode, made by Libelium. Knows both European and US frequencies. Programmed in C and C++, it's compatible with Arduino or the Raspberry Pi. It's a really small microcontroller and the sender on it. Also you have the M.Dot, which seems to know all the three frequencies, but it's a little more expensive. So these are not the only ones. There's a lot of LoRa devices. These ones are the most common. The ones that we will use is this LoPi and this LoRa GPS hat. For a gateway, when it comes to gateways, well, these are expensive. So you can buy expensive gateways from well-known manufacturers for probably 1,000, 2,000 euros. So that's an expensive gateway, but that's an industrial one. So this is the gateway that a network operator might install on their antennas. A low-cost gateway, which knows 8 channels at a time, meaning it can scan the frequency and talk to 8 devices at the same time, is this IMST IC880A. This one connects to the Raspberry Pi via SPI. It's about 200 euros, and it's capable of a decent amount of transmission. So if you want to make a do-it-yourself gateway, I think this is the best idea. More important, because we're in Europe, this one is produced in Europe, so it's easy to get it shipped. Okay. If you have any questions. So remember, LoRa is only the transmission of data. So it takes a stream of bits, encodes it, and sends it to the air to a receiver. That's all that LoRa basically does. It's a best effort transmission, meaning it will transmit the data, but it never cares if the data gets to its destination. Is this clear? So it's like UDP. If you think of a classic network, it's like a UDP transmission. It never has control or acknowledge. So this is LoRa. Using LoRa, you can transmit whatever information you want to some other device. If you want to place that on an IP network, it's your business to build software around it. This is the first experiment that we are going to do, and it's going to be just to send some data over a wireless transmission. So this is LoRa. So if you hear of LoRa, it's only a transmission method. LoRa WAN, LoRa Wide Area Network. LoRa Wide Area Network is a layer on top of LoRa. It's basically software and a set of rules that allow devices to send data, get an acknowledgement that the data has been sent, and maybe send the data once again. So LoRa WAN, first of all, makes data transmission reliable, meaning the node knows for sure that the data went to its destination, and also transposes the information to an IP network. This is how it works. So you have the Semtech microchip that will actually encode the data and send it into the air, depending on the continent that you are in. It has the LoRa chip, which will actually add some bits for control and error correction, but only forward error correction, meaning only the receiver is able to correct errors. If the receiver is not able to correct errors, like the error in the data is so large, that's it, it will drop the data. LoRa WAN is another layer on top of this, and this is done by the LoRa Alliance, meaning a set of rules and a set of software that specifies how the payload of this LoRa needs to look like. If you know classic networking, this LoRa layer is the layer 2 in the network, meaning just the data transmission, and LoRa WAN is the layer 3, it's the IP, and also layer 4 transmission protocol. So this one makes sure that data is arriving, we don't have duplicates, and everybody that sends data knows if the other one got the data or not. On top of this, we have any application. The application usually resides on the network. So let's see how this works. We have a lot of LoRa sensors scattered around in a city, for instance. We have several gateways on top of buildings, and these sensors will send data. Several gateways will actually receive this data and send it to a server. The server is a piece of software that runs on the normal network stack. So these gateways have LoRa on this side, and on the right side they have a normal IP network. They send the data to a server. The server gets the data, but it's not only the useful data, it's also some information about the number of the packet, the destination, the type of the packet. The server will be able to filter out duplicates, because as I said, a sensor is sending the data, several gateways might get it. They both send the data to the server. The server will decide which data is the first one and drop the duplicates. This is important to have several gateways, because some of the gateways might get errors in the transmission. Like there was some interference. The building has too much metal and the gateway doesn't understand the data correctly. One of these gateways needs to get the whole packet and send it to the server, and the transmission is already okay. From the server, this is sent to an application server, and this can be a graphing interface, this can be some business logic server. But this side, this is a normal IP transmission, normal network transmission. Backwards, from the application server, this is sent to the network server. The network server decides which gateway is the best for sending the data to the sensor, sends the data over IP to the gateway, and the gateway sends the data to the server. If it doesn't get an acknowledgement, the server will retry several times. But the transmission from the application to the sensor is done via the server and one of these gateways, because the sensor is not capable to filter out duplicates. Is it clear? If you have any questions over here. Besides this infrastructure, LoRa WAN also adds encryption. So data is encrypted over the network. In the normal LoRa layer, there's no encryption. Data is just sent. This provides encryption. This is a more formal model on how LoRa WAN works. We have here the application that runs on the sensor, meaning on the microcontroller. This one decides that it needs to send some data. It goes to the device that knows to send LoRa, but before that, it adds some LoRa WAN headers. It adds the information for the network, it sends it to the LoRa device. The LoRa device is going to send this to the gateway. But the information that goes to the gateway is encrypted twice. First, the application on the microcontroller will encrypt the actual data, the sensor data. The layer below, the one that makes the LoRa WAN communication, meaning the destination address, the application address, so on and so forth, will encrypt the data once again and send it to the LoRa device. The LoRa device sends it, it gets to a gateway. The gateway gets the information, knows where it needs to send it to over an IP network, and sends the data over a normal IP network to the server. The server has the other side of the LoRaWAN layer, which decrypts the data that was encrypted, decides which application needs to get the data, and passes the application up to the stack, passes the data to the actual application. The application is responsible for decrypting the useful data. So this is completely secure. The gateway has no idea what data it sends. The actual payload is not visible. Not even the server, the network server, knows the data. And this is important because anybody can put a gateway. Please look at this device, this network. If I want to put a LoRa gateway, I'm just installing a LoRa gateway. If I have a LoRa gateway, because the frequency is open, I will get my messages from my devices, but then again, I will get every LoRa message that somebody is transmitting. Is this clear? So the gateway in a normal network shouldn't have the ability to actually inspect the data. The data needs to be completely encrypted, because otherwise I could actually see your data if I control a gateway. So my data is encrypted and your gateways will get it. My gateway, your information is encrypted and my gateway will get it, but it will just send it over to the network. And it's the application layer that will decrypt the data. Is this clear? So LoRaWAN devices are divided in 3 classes. Like if you use only LoRa, that's okay. Like you just send data. But LoRaWAN defines the way that devices should behave in order to save more battery. So devices are divided between 3 classes, A, B, C. Class A is sensors. These are battery powered. They need to last at least 2 years or more. They basically sleep most of the time. They collect some data, send it over, and sleep. Again wake up, collect some data, send it over, and sleep. So the device is not doing anything most of the time. This is why the device is able to preserve battery life. In contrast, devices from class C are always on. So they are connected to a power source, they can transmit and receive data all the time. So basically they are normal network devices. The problem with A-class devices is not when they send data, because this is really easy. How do they receive data? Because if a gateway or an application wants to send some data to the device via a gateway, if this one sleeps, it's not going to get the data. And if this one sleeps most of the time, the gateway needs to know exactly when the device is on. So there's a set of rules on how you can do this. Class B is a combination of the two, meaning it's a battery-powered device, but the way that it sleeps and when it sleeps is controlled by the network. So LoRaWAN provides some control messages, and the network can actually instruct the device when to sleep and when to wake up. Class A devices sleep whenever they want. Class C devices never sleep. Class B devices are a mixture. These ones are not supported by most of the systems yet, because this is new. So how do we send data to an A-class device? For the C-class device, this is easy. Like we send data, the device gets it. This is the gateway, basically. Class A devices, this is more trickier. And this is how it works. The device transmits some data, waits a time that is called receive delay, and tries to receive some data. If it has some data, it reads it. If there's no data, it sleeps again and then has a receive delay too and tries again to receive some data. If it doesn't receive any data, it just goes to sleep. So when a gateway wants to transmit data to a class A device, it needs to do this right after it gets data from it. This delay is defined so that the network has time to get the data from the gateway and build a response. So the second delay is for slower networks, which take longer to take data and make a response. But the network needs to know if it's a class A device that it can send back data to the device only after it receives a transmission. So if you have an application that sends data to a device, the network does the following: makes a queue, queues up the data, and whenever the device wakes up and sends some data back, sends some data to the network sends a reply. Is this clear? So this is how devices can preserve battery life. But this is tricky, because a device might sleep for hours. So when you design applications, think twice if you really need to send data to a device. Because if you send a lot of data, the queue is getting longer, and the transmission window is really small. Like, it will do one transmission and that's it. And this is a second transmission and that's it. After a certain amount of time, the device is not going to try to get another transmission. It just goes to sleep. So if you don't send the whole queue, you will send the next message in an hour. And you have a lot of messages. The message that you send today might get to the device tomorrow. Is this clear? For Class B devices, this is solved because you can instruct the device not to go to sleep until you clear the queue. For Class C devices, as soon as you have a message, it goes to the device. Is it clear? So parameters. For the LoRa WAN network, you have the parameters from the LoRa transmission device plus these ones. Each device has a device EUI. That means a unique ID. This is written inside the device by the manufacturer. This is similar to what from the IP network? To the MAC address, right? Okay. Each device will get a dynamic device address once it connects to a network. So not when it sends LoRa data. Sending of the data does not have this address. But when it connects to a LoRa WAN network and respects the rules of the LoRa WAN, it receives a 32 bits dynamic address, which is not unique. So there might be several devices that have the same address. It also has an application EUI. So each application that you make has a unique EUI. This is similar to the port from the network, from the IP network. So each application has an application EUI, and each gateway has a gateway EUI. So that when a gateway receives a message and sends it to an IP network, the IP network can make a difference between several gateways and see that it gets a message from two different gateways, the same message. So these are the 4 parameters that you really need. This one is written inside the device. These ones you decide. Usually the gateway EUI is something that you set on the gateway. Sometimes it's the MAC address, the real MAC address from the gateway plus some bits. Application EUI, this is your business. This is something that you need to configure the node. Now, how do you join a device into the network? There's 2 ways. Either activation over the air, or over the air activation, OTAA, either activation by personalization, ABP. The second one is easier but less secure, meaning you know the device EUI, you set the device address up front. So on the network interface, you set the device EUI, and you set the device EUI on the device. So it's your business to give it an address. And you get a shared network key and a shared app key from the network. But you have to write it into the device. So when you deploy a device, these things stay written until you change it. These network shared key and app shared key are used to determine the encryption keys, first of all, for the network, meaning the data that goes to the network and is read by the network, which decides to which application it needs to send the payload, and the application shared key for the actual payload. This is less secure. If somebody breaches these keys, all your devices are compromised. Is this clear? So once you write these into the device, you need to reprogram all the devices if somebody breaches your key. But this is easy. Like, all you need to do is to set these parameters, and the device is automatically joined to the network. Like, it sends data and the network just gets the data. You can compare this to what in the classic IP network? To the static IP. Like you just write an IP address, a gateway, DNS, and that's it. The second, over-the-air activation, requires only 3 parameters. Device EUI, which is written into the device, an application EUI, which you get from the network, but which doesn't have to be secret, and an application key. Now, this application key is secret, but that's a key used to actually get all these information. The device connects to the network, sends some connecting messages. The network decides if the device is authorized to enter the network based on the device EUI and the application EUI, and generates these 2 shared keys and sends them to the device. If these get compromised, no problem. It just makes new ones and instructs these devices that they need to do the authentication once again. Devices will be able to change these keys. Is this clear? This is more secure because it doesn't leak anything. Is it clear? Okay. You will say, okay, if I have the application key, this can be compromised, right? If you compromise the application key, it's easier to change only the application key, and I think this one is changeable by the network. So this is a better way, but this is more complicated. In our case, the case that we will do today, we will have to use the second one. This is because our gateway will not be able to send data back to the sensors. Like the gateway that we have, the software that we have for the gateway is not capable of receiving data from the server and sending it to the devices. So this one requires that. This one does not. So this is what we are going to use. For our purpose, this is super fine. If you buy a normal gateway will actually know how to do this. Okay, so this is LoRa and LoRa WAN. Remember, LoRa is just the transmission way, and LoRa WAN is the transmission way plus some software and some rules to be able to make a secure network, and a secure network that will communicate over an IP network as well. If you have any questions.